Welcome back, guys, and wow, I've got some news for you. I'd always resisted using online models, but I found out that the cost was actually very, very small, certainly for the sort of stuff I was using. It's like in a cup of coffee a month or something like that, maybe type of type of region. So I decided to add them to my autocoder, which is not difficult to do. So if you remember the last video, I had a 30 billion weight one, which was local in the sense that it only runs 4 billion at a time. Well, I thought, well, let's just go for broke and go for the big ones. So I put in the qwen one, the really big one, which is for 400 billion. And then I also went for the Claude Sonnet one as well, which is what a lot of people. And the Claude Sonnet 4.6, or is it 4.6, is ranked number one. Is about 80% success rate, whatever that is, of the tests they do. And second is the qwen one that I just mentioned, the 400 billion. There's also DeepSeek ones. I haven't even tried them yet, but I just want to show you what I've done so far, what they have done so far, I should say, how incredible the results are. And I'm talking about things here that work first go as well. I'm not talking about something I've laboured over, it's had to do it like 10 times or something. This is first time. So let's just look at I'm not going to bore you with going over the code. Let's just look at some simple ones from the ground up. The first one I started was this morning was using the qwen one because it wouldn't work with a 40 billion one. So the 400 billion one, I did a world clock one, which is that's not exactly mind blowing, but I thought it was quite good. So I can get the time. It's the time in Auckland at the moment. It's Wednesday, the 4th of March 2026. In Sydney, it's 11:15 in the morning. In London, it's yesterday. It's quarter to one midnight. I suppose I should put the whether it's AM or PM or whatever. But anyways, so it's a world clocks. So I did that one, and then one of my ex-colleagues said, "Why don't we do a calendar? Try that one." And it wasn't very successful. I did that with the 40 billion weight ones, but now I did it again, this time with Claude Sonnet, and I ate it for breakfast. So this is the calendar one it's produced. It was just like first go. It's like, what's a calendar? So today I had an appointment. I've already got doctors. I say shopping. There we go. So that's the calendar. Looks really nice, and I think you can delete things anyway. That you can go April and so on, different months of the year. It's got the appointments down here. So that's that one. Then I started using it for what it was really intended to be used for scientific purposes. I went back to the PID controller one, and I got. Now, which one was this? Oh, it says at the top. Yeah, this is qwen3. So this is just the 30 billion one, 30 billion weight one. So this one was run locally, and I put in the structural resonance. So this is the example that's in my book. Cut to my book. Back again now. So this. Has got a structural resonance. So this is a PID example, like a real problem you get in industry, where you almost have something that restricts the bandwidth of your system. Electromechanical systems is usually a structural resonance. Like if some of the fastest hard disks in the world, some of the fastest servers in the world are hard disk drives with enormous bandwidths. And the structural resonance stops you from making them, as wide as well. There's lots of things, but the structural resonance stops you from getting, even higher bandwidths than you'd want. So that in real life you can't just put PID values anything you want. You can't just say, "Oh, I'll increase P to 1,000 or 20,000 or 30,000," because something gets in the way and stops you. It's like the rules of the universe. Anyway, here's it working on there's the error. I needn't have bothered because this system's already got an integrator built into it. So it's like a motor plus a structural resonance. But I wanted you to show you guys this. If I increase the proportional gain, it gets quite nice actually. But if I want to put another second integrator, two integrators is always better than one. Notice how I get the ringing and goes down. If I introduce derivative action, which dampens it, then I should run into the structural resonance eventually. Oh, there it goes. So what you're seeing here is this is the structural resonance that's causing this, not the if you like the Nike the first Nyquist one. It's like it's got two crossings on the Bode plot. Again, you need to read my book to look at the details. You see that rather strange response. So that means I shouldn't be operating in that bandwidth because I've hit the structural resonance and it's starting to ring all over the place. So that's not the normal instability. If I just, the normal instability is like this, if I just put an integrator on its own, then that's the first crossover, gives you instability. It's ringing at that frequency. Anyway, so that's the PID. And then what did I do? Oh yeah, I'm just playing around. I thought, I wonder if they'll be able to play a tune this time and actually get it right. So this again is the qwen3 coder. I think no, this one is the cloud version. Let's have a look. Twinkle twinkle little star. The notes look right, but I haven't checked them. So that's an easy one anyway, but still 100 lines of code. Got more sophisticated then. I thought, no, I can't remember the way I did it. Yeah, this one is incredible. I moved on to Claude Sonnet. I said, let's give it something really tough. So I give it a problem of FM, frequency modulation, to simulate it. How about this? Sounds like something out of Lost in Space. This is FM. This is phase lock loop demodulated FM. This is the baseband signal. Input a square wave. Triangular wave. Put the frequency up a bit. See the triangular wave, the FM waveform, and the demodulated waveform. I'm going to stop this because the noise, how do I turn it? One thing I didn't put in was the noise to turn off. But what you're seeing here is a 2F carrier feed through of the phase lock loop. Okay, that's standard. You could filter that out, but it's twice the carrier frequency in a phase lock loop. This is how your FM radio works. I never thought I'd see one running on a PC like this. So that's a phase lock loop demodulating FM. And I did a slightly simpler one, but I did this to see how good it was at drawing as well. So this is just an RLC circuit, but look at the lovely diagram it's drawn for the RLC. So it's a square wave, and I can vary the resistance. This is pretty straight. This would be like second year at uni or first year. And as I make the resistance bigger, it becomes more damped, and the output follows the input. As I make the resistance smaller, I get underdamped response. We can do the equations if you're really interested. And eventually, when I've got no resistance, it's just a tank circuit just ringing. Yeah, how useful is that for, actually tells you the damping factor here and the resonant frequency, 500 hertz. I didn't even put that in, it's stuck all that in, it's smart enough to work all that out. Did that. Perhaps not such a good one, but very tricky was, oh, I can't find it there, I'll get back to, it is here somewhere, is, well, where it is, I think it's further along anyway, we'll get to it. Foucault pendulum, I don't know if you know the Foucault pendulum. It's also a way of determining the rotation of the Earth. I thought it's never going to be able to do this one. My God, it could as well. So this is a Foucault pendulum simulation. You can see it changing as the Earth rotates. That's what a Foucault pendulum does. And to be absolutely straight with you, I'm not really sure what the other things are. I know where the phase portrait is, that's position versus velocity. Some of these other things, I'm not quite sure what the hell it's doing, but you can see the simulation of the Foucault pendulum there. Oh, it's not actually showing it vertically, but unfortunately it can't actually, oh yeah, I can move it. Oh, didn't think I could move it. Oh, that's quite impressive. Anyway, so that's the Foucault pendulum. We used to have one at Massey in Palmerston North. So I've got that one. Done the calendar. Done the PID controller. Oh, okay, so here's another one. This one didn't work out as well as I thought it was. But I was just to see if it would be any good for teaching. It's not quite that great, as you can see, because it's probably the way I explained it, but it's to explain Kirchhoff's voltage law. And it's not quite got the equations labeled properly. I just left it at that just to see what it could do. I thought it's going to be it's not going to get this one right anyway. I thought it's such a lot of code to do this, but this is a two mesh system, and I just asked it to show the flow of current. I guess that current could go in the other direction if you wanted it to, combining, and it gives you the equations and works out the things, but it's not that great. It shows you the voltages as well, so that could be improved upon, but that was Kirchhoff's law. Then I did this is an easy one, similar to the RLC circuit. Nice diagram. That is the mass spring damper if you're a mechanical engineer. It's not quite so well animated, but it's here. As I put the damping down, it becomes more like an oscillator. That's like the resistor I showed you earlier. And then as I increase the damping, it becomes more damped. Now this again here is the phase portrait. That's displacement versus velocity. What you're looking at here is what's called the equilibrium point. That's where it settles down at, which is 0. In this case, it's a linear system, so it doesn't. In nonlinear systems, you can get more than one equilibrium point. So here it's linear. If we put a nonlinear spring in or something, then we might get some funny results and chaos and stuff. Oh, which reminds me, there's another thing to show you. And this was done on, again, I'll be able to see on what was done by. This was done by the 400 billion parameter one. It was a double pendulum, not inverted, but a double pendulum which exhibits chaotic behavior. And there's the trace of where it's going. This is using MATLAB plot library. It's not MATLAB, it's the Python MATLAB library. Quite incredible. This is the phase portrait. I did ask for this, but I'm not sure anybody's ever done this before, but this is a two-dimensional phase space trajectory. You normally don't do this because it's three-dimensional phase space trajectory. Normally it's two-dimensional, like I showed you earlier, but this is the position of theta 1. It doesn't say what theta 1 is. I assume it's the angle of the top linkage versus the speed, the velocity of of the top linkage and the velocity of the second linkage, and that's the so it doesn't tell you a lot because it doesn't, mind you, it is chaotic, which means it's never really converging to any one what's called an equilibrium point. So anyway, that's a double pendulum. Just did that, again, got it first go. No, was it second go, that one? Now some one more control one and then some fun ones. So this was amazing. Poles, so some of you may know if I taught you out there anyway, because I don't think it's covered in many courses. Why are poles in a linear system so called? The answer is because if you plot them in 3 dimensions, you get something looking like a pole like this. So what you do is you if you're looking down on this is the Laplace domain like this. This is the Laplace domain. So if I'm looking down on top, imagine looking down from the top here, you'd see these 2 poles, the x's. But if you plot the magnitude in the z plane in 3 dimensions out of that, you get these magnitude going to infinity at the pole. But what I did was here is I can vary them, and so I can move them around, and I actually didn't put the step response. I should have put that in as well. I could still do that, but I'm looking at the frequency response. So as I get nearer the j omega axis, you should see the resonance, see how it goes going up to infinity at the j omega, and look how the phase shoots down to minus 180, very sharp phase. And that's a more damped system as I move in the other direction. If I go unstable, you don't notice it because there's no time domain here, that's only frequency domain. So in the frequency domain, there's no such thing really as instability. That's a concept of the time domain, because you can still plot the frequency response of a unstable system. You see, you're none the wiser. Although the phase goes in a different direction, it's gone off the screen there, the phase, but you can still plot that. And there's so anyway, I thought that was quite interesting. Again, it did that first go, and that, how many lines of code is that? That's 500 lines of code. Okay. And now, Space Invaders. I thought, let's do a decent one. I didn't quite get this one right. I didn't bother to do it a second time. But it does look like an arcade game. When you look at it, it's got all this stuff. Yeah. Oh yeah, see it kind of hangs up. But it does sometimes work a little bit, but we can, that can be worked on. Yeah, you see the problems there. So I didn't bother pursuing that, but I moved on to Pac-Man, and boy, what it produced there. Again, first go. But I'm not very good at Pac-Man. This version is so fast, I think you need to be Superman to keep up with it. Fortunately, it produced, even as the correct sounds and everything, so it produced a second version, which was a bit easier to actually keep up with. And, well, as I say, I'm not very good at it. Need a... Oh, got caught again. Oh, that's me over. Let's just try again. I'm just having difficulty control. I was never very good, even in the pub when I was a student, when it came out. Oh, there you go, I got one. Right, so that's Pac-Man, which I think it's got multiple levels as well. So this is a proper Pac-Man game. 947 lines. So this was produced by Claude Sonnet 4.6. Again, didn't take it, I don't know how long it took, a couple of minutes to produce this code. Can you believe that? A couple of minutes. And did it. Lastly, I think we did Space Invaders, didn't we? And that's it really for the time being. Just showing some quite incredible coding that these things produce, and the level from going from Ollama models, which are quite small really, and you're having to put in all the error correction stuff in to these online models. You still need this framework, so nothing is wasted, and we're still using the same program. It's just that instead of selecting a local Ollama model that I've downloaded, I'm selecting a cloud model. And the cost is very, very cheap as well. So it's not like it's going to cost you a fortune. But of course, the bigger the code that you're producing, the more you're charged. It's a fantastic thing, though, for little scientific things and teaching, I think, this kind of thing, especially the Claude one. Thank you.